But first, let me point out a few features of this design problem. It's not trivial because we see that S0 appears in both the numerator and the denominator. So in other words, okay, your first impression might be, let's pick an extreme value, like all 0 or something. So if we make h, all the values of h very small, well, that certainly, actually, let me back up for a second. What does IRF-C look like? IRF-C looks kind of like this. And it is in fact a decreasing function. So if I want to minimize this, I want to make this argument as big as possible. I want to get all the way over here. So we might think, okay, let's make h as small as possible. Well, that makes the denominator really small, but it also makes the numerator small. So it's not really clear what'll win. And similarly, if we try to make all the elements of h enormous, that makes the numerator really big, but it also makes the denominator really big. So it's, again, not really clear what wins. Okay, find h star I, which is argmin over h I, for all possible at h hat I, 1/2 IRF-C of 1 minus alpha S0 divided by 2 root 2 sigma squared. Okay, I argued a second ago, IRF-C is a monotonically decreasing function. So that means if I want to make IRF-C of x small, what do I have to do with x? Basically, I have to make it enormous. So as x grows, IRF-C gets smaller. Yes?
Question. Why don't we just take a derivative that we did for z?
The problem is that h is a vector. So because h is a vector, we would have to take the gradient over all of the elements of h. And in fact, the number of elements of h is not fixed. It's ND, which is itself a variable. What I'm going to show is that we don't have to. There's a result called the Cauchy-Schwarz inequality that lets us totally bypass that. So this is actually much easier to do it this way. Taking the first derivative is probably your first shot if you want to optimize with respect to a scalar, like z. Z is just a scalar. Later on, we're going to do that also with alpha. But we can't do it here, or at least not easily. I mean, it's an option. We could definitely do that, but because h is a vector, it becomes a lot more complicated. Okay, IRF-C is monotonically decreasing, so if we want to decrease IRF-C, we have to jack up x. So this problem is equivalent to saying, and again, remember, I don't care what this probability of error is. All I care is about setting, finding the minimizing value of h. So I don't really care what the exact value is once that value is set. So h star I, if the argument that minimizes this expression should also be the argument that maximizes the expression of the brackets. So I can say this is also equal to argmax over h hat I, 1 minus alpha S0 divided by 2 root 2 sigma squared. What else I can do? These constants don't make any difference. So because I'm multiplying by constants, because they're positive constants, I don't. It doesn't really make any difference to the argmax. changing h only changes S0 and sigma. It doesn't change the constants. I can throw out the constants and have the same problem. So if the maximizing value of h doesn't change with this constant, similarly I can square this, and it also doesn't change the maximizing value of h because square is monotonic. So if I find over all possible filters, over all possible time index permuted filters, the value that maximizes S0 squared divided by sigma squared, then I will find the filter that minimizes this expression. Why? Because if I maximize this, I'm maximizing the square root of that, and I'm also maximizing the square root of that times a bunch of constants. And if I maximize that, then I'm minimizing curve C. Okay, what is that? What is S0 squared over sigma squared? So we've simplified our expression down to h hat star of I is equal to r min, or excuse me, r max over h of I. S0 squared over sigma squared. And now I can substitute these in. Is equal to r max over h hat I of the sum over I. I, h hat I squared divided by n0 over 2ts sum over I of h hat of I squared. And again, I can do the same trick. This is just a constant. It doesn't really affect if I maximize this expression with respect to h hat.
Sorry.
Yes?
Do you have to put, do you have to like somehow mention that summation that can be or each ITQ?
Yeah, so it'll turn out that, yeah, we may as well just put that in right now. I equals 1 to NB. And the reason is, suppose, is it possible for the maximizing filter, so S0 is always 0 outside the range from 1 to NB. So is it possible that the filter that maximizes this would have elements that are beyond 1 to NB? The answer is no, because those elements would just be multiplied by 0. So they're obviously irrelevant. So we can restrict ourselves to the summation over I equals 1 to NB, and we can believe that h hat must exist only over I equals 1 to NB, because if it doesn't, then those elements beyond 1 to NB just get wiped out. Okay, but the same argument I did down here, if I maximize this, if I choose h hat that maximizes this expression, then I also maximize the same expression, getting rid of that constant. So basically I'm just going to rewrite this without this constant in the denominator.